Hi, thanks for attending this talk. I'm Paul. This is Kishor, and we're going to talk about a joint collaboration on OpenJDK between Intel and Oracle on something called the Vector API, not Java util vector. You're in the wrong place if you think it's about that. So what is this? So the Vector API is about enabling developers, advanced developers, to code cross-platform computations leveraging hardware data parallelism. What do I mean by that exactly? So I'm talking about SIMD instructions. I'm talking about AVX on x86 and Neon and SVE on ARM. At the moment, the JDK, I don't know what percentage of instructions it leverages on the CPU, but I would say there's a lot of dark silicon and a lot of very interesting instructions that the JDK and JVM could leverage, but doesn't at the moment. And this API is about leveraging some of those instructions very explicitly. So the goals of this API is we need to get a clear and concise API to express these kinds of computations, but because it's Java, it has to be platform agnostic. We can't just code it up to x86. We have to make it work on ARM and potentially other forms of computation devices in the future that don't exist yet. And it has to perform reliably. So when you express these computations, you've got to have confidence that it will produce the right instructions for you and get great performance out of it. But when the right instructions aren't there, it has to gracefully degrade, preferably to the equivalent code that you'd have written if it was a scalar computation. That's the challenge we have. That's going to be a difficult one to achieve, though. So the motivation here is there's an auto-vectorizer already in Hotspot using superword analysis. This is actually pretty complex to enhance in C2. And in general, auto-vectorizers, when they work very well, but when they don't work very well. They're kind of fragile. And in general, transforming scalar code is an ongoing area of research, which is actually quite hard to get right. We've seen this with parallel streams as well. We can get some of the way there, but to transform scalar code into parallel code, whether it's data parallelism or running over multiple threads, is hard because there's assumptions in the scalar code that make it tricky to do that in general. So the Vector API and auto-vectorization, they're not actually mutually exclusive here. They can benefit each other. So the work that's been doing to support the Vector API, adding a bunch of support for instructions in Hotspot, is also applicable to the auto-vectorizer as well. So it's actually, we're building up the platform in Hotspot more generally and providing an explicit API, and yet we can, when we infer the scalar loops, we can actually benefit from that as well. So we're raising multiple boats are being raised as we're raising the level of Hotspot's water, if you like, bad analogy. So this is really for advanced developers. It's not for everyday developers, this API. It's for developers that know what they're doing. It's for developers in the JDK itself. And those developers who write popular libraries that many other developers use. So one way we win here is we get the advanced developers using this API, and then they produce libraries that others use, and we get the network effect coming in. And so this is for stuff like machine learning, cryptography, hash codes, and lots of use cases in the JDK, Java on Java itself. And that will, if we can leverage this within the JDK itself, I think it helps us code stuff more efficiently, faster, and safer. So there's a big strategic motivation here, and that is in conjunction with value types. We want to make the Java platform a really great platform for numerical computation in general. So I'm going to go for a simple example now. I'm going to show some vector code. Just going to dive right in there and show it. So I'm using JMH as a benchmark here, and we have a vector loop. So what we're doing is we are looping over an array. We're striding over an array by a certain length. We're loading a vector from an array, from array A. We're loading a vector from array B. And then we're doing an expression on it. And this expression is expressed explicitly in code here. We have no operator overloading in Java, so we have to express it as methods. So we're saying we want to multiply an element in A by itself, multiply an element in B by itself, add them together and negate it. Why? Because I just chose it. There's nothing particularly special here. And then we loop round this thing. So we're loading a chunk of data at a time, not one element at a time. We're loading a chunk of data at a time and doing work. So what happens if we compile this and run it using JMH, and let's look at the assembly output. So I'm going to run this using dtrace-asm on the Mac, which is going to sample the program counter of my program when it's running. So unfortunately, given Mac's security box stuff, sandbox stuff, I have to type in my password. So we're running our performance measurement here in JMH. We're doing some warm-ups, we're doing some iterations, and we're sampling the program counter of a benchmark. And then we're processing that information output from dtrace, matching it out to a printed assembly that JMH configured to print out. So if we look at the output of this, we should see some hotspots in JMH. And if you can see this, we should see a hot loop in JMH here doing some work. Can you all see that? So we see a vectored load using a YMM register. So I'm loading 8 floats at a time. Loading A, loading B, multiplying A, multiplying B, adding the two together, doing a weird negation using XOR, blatting the bits in, vectorized as well, 8 floats at a time, storing it back into my result array, looping around 8 times and back again. That's my vectored hot loop. I turned off loop unrolling so you can see it better, but it will loop unroll as well. So there's a very clear translation between the vector API that I showed there and the instructions that it produces. So that's just showing. Now, does it perform any better than the scalar loop? No, it does not. So perhaps we can all go home. No, the reason why is the auto-vectorizer does pretty well on simple cases. This is not really designed for simple cases. It's designed for more complex cases. But even in the simple cases, it should do as well as a vectored loop. We have some investigation to do here to see why that might happen. My suspicion is it's due to alignment. When you load vectors, it's better if they're aligned according to their size, and if they're misaligned, there's maybe a performance variation there, but we have to investigate. But this fits to the goal of graceful degradation. You should be able to use the vector API and trust that it's going to get good performance, as good as the scalar loop, or better if you're using more complex calculations. So I showed some types there, the float vector. So all we have is a general vector type with 2 generic parameters, t and s. And down on the vertical side, T stands for element type. We have byte short, integer long, float, and double. And on the horizontal side, we have shape. And shape is essentially the size in bits of this vector. And given those bits, how many bytes, shorts, integer longs, or floats can I pack into this vector? So we have a byte, and we have 512 bits. We can pack in 64 bytes into that vector. If I have a double, I can only pack in 8. And if you're familiar with x86 registers, you'll know how those map, and we'll talk about that later. There's a hierarchy. We have a vector type, and we have some subtypes of that are specific to our byte, short, int, long, and float, so we can express calculations in terms of bytes, ints, longs, and so forth like that. And we have some internal implementations that are specific to the shape itself. So the overview is a vector has an element type, it has a shape, with explicit type specializations and specific type operations on there. So a float will have operations like sine, cosine, and so forth like that, but an int vector would not have those operations that don't make sense. And vectors are instantiated using something called a species, which just think of it as a factory that gets you an instance of a vector from an array, from a constant, or something like that. I've glossed over this a bit because I want to show some more examples. So the status of this API is it's being actively developed under OpenJDK Panama, under the vector intrinsics branch. In the appendix, there's some details of how you can go and build this yourself. It's a candidate JEP, which is going to propose an incubating API. And an API will be planned for review soon. And it will incubate for many releases. Why is this? We want these vectors to be values, and ideally you want to generify over them so we don't have to do this specialization in the future. But that's going to take a while to get there. We want to say value vector net, and then we don't have to have byte, int, and short vector explicitly. We can just have one type, and then we can have conditional methods based on the type. But we're not there yet. It's going to take a while to get there. Here's another example, hash code. So can we vectorize hash code instead? This is a bit more complex, and we'll get a bit more performance out. So if you're familiar with how the hash code of arrays work in Java, this is the hash code algorithm for arrays and for lists. Unfortunately, we can't change it because it's specified to be like this. This is not a particularly performant algorithm, but we're stuck with it. But can we make it performant? So this is basically polynomial. calculation. So how would we go about vectorizing this? Well, if you look at it, I can explicitly unroll that calculation by 8 times by just making things constant and multiplying in the array by just zoop, unrolling it like this and cleaning up the tail afterwards. If you notice, there's some common pattern here. I'm doing a sort of each element in the array is being multiplied by a constant and then added. We can see some common patterns here. If we extract that out, we see we've got a bunch of constants. We see we've got an intermediate result and doing multiplication, and then we're doing some catch-up, summing up, and multiplying by a constant, adding, and then looping around again. Essentially, what we want to do is turn all those 8 operations into 1. Turn 8 instructions into 1 instruction instead. How do we do this using the vector API? Well, here's an example. I'll try and go through it. So what we want to do is we want to use a byte vector, and we want to load 8 bytes at a time. So that's 64 bits. And we want to stride over the array 8 bytes at a time. We want to load the byte from the array using our factory. And then we want to cast the byte to an int. So we don't want to perform our operations using bytes because we want to overflow an ints, not bytes. So we're casting each byte to an int. So we're going to cast it from 64 bits shape of a byte vector to 256 bits of an int vector. So we're packing the same number of elements in. And then we're doing our multiplication by a constant. Then we're summing all those up, and we're going around the loop again. So is that fairly clear? Clear as mud? No? There's a problem here I'll get to later. There's a reduction inside the loop, which means that performance won't be as good as we want it to be. Here's the example of how I generate the constant vector that I use for multiplication. I just create an array, and then I create my constant vector from the array. Now, this example here is specific to an architecture. It's specific to an architecture that supports 256. But what happens if I take my code that supports my laptop and I run it on a system that supports 5112 bits, AVX 5112? Then my algorithm isn't going to perform as good. So you can generify this so that it can work on my laptop, but it can also run on a server-side system running 512 bits instead. So you do not have to encode your algorithm to the specific architecture, and that is key for getting this to work on architectures like ARM as well, which have variable length vectors that are runtime specific. So it's exactly the same algorithm, just generified. And there's some examples of how you create this that I'm not going to go into in detail for time. But the key takeaway is you can get a preferred species or factory out that is optimized for the maximum vector size that you can support on your system. So what's the performance like here? Well, the hashcode 64 vector supports is better than the scalar loop. I showed the top number, 282, is better than 779. And the generified version is exactly the same in terms of performance. There's no cost to generifying here. But the scalar loop unrolled version is terrible. Why is that? There's something wrong going on there, something suspicious. Well, for some reason, Java-C does not turn all of these constants here. It does not calculate that expression, and it puts all these multiplications of 31 into the bytecode directly. So I've got to help Java-C here and actually turn them into constants myself to get a real performance benchmark here of this unrolled. And if we unroll that, we get a lot better, but still not as good as the vectorized one. If we want to go further here, there's a great blog by Richard Startin. Now, Richard is one of these developers that this API is targeted for. His blog is excellent. He shows some great use cases of this API, and he's getting some interesting results out. This is fantastic. So he has another algorithm that allows you to pull out that reduction that I showed in the loop that's slowing things down. And you've got to remember this is a polynomial, so it's addition, it's on ints, so we can basically group in any way we want to create add the numbers up. And you can iterate in reverse. You don't have to iterate forward through the array. And if we use Richard's algorithm, there we get a value here of 88 instead. That's a fantastic performance result, speeding up particularly for hash code algorithm here, but we can get really good results here. And this is a type of thing we could put into the JDK to improve this existing functionality. He does some very interesting stuff. There's a slide at the end which shows the code, but you can go see it in his blog as well. So what about conditional expressions? So here's some scalar code. All I'm doing is I'm looping over two arrays here. And if the value in the A array is greater than 0, then I add the two together. Otherwise, I just assign the result to A. That's pretty simple. The vector code is down below. So how do we do this using a vector API? We use something called masks. So we're loading a vector from A, we're loading a vector from B, like before. And then we create a mask. We say, is all the elements in A greater than 0? And we get a mask back. And if it's greater than 0, then the bit is set. And if it's less than or equal to, then the bit is not set. And we can apply that to the add operation here by passing in a mask, which says, apply the operation if the bit is set, don't apply it if it's not, and just pass me A all the way through. And then we can store it back again. So how does that perform? So the generated code in this loop looks like this. So remember, we load two values in. Let's have a look what we're doing there. So what we're doing is we're loading a value in, we're adding, we're comparing, and then we're doing a blend. And the blend says, blend these in based on my mask value, and then store the result back. So we're not actually using any mask registers here because we're not on an AVX512 system which has mask registers, so we have to use something else, which is the blend operation. So the performance here is quite remarkable because the auto-vectorizer is not so good at doing conditionals. We could probably teach it to do that. That might require some work, but out of the box, the vector API performs a lot better because it can use these techniques, whereas the auto-vectorizer can't. So as a lesson here, we can have operational composition. So what we can do is that we can build up our mask-accepting operations on the vector API as a composition of the operation plus blend, and that's exactly how they're all implemented at the moment. We could teach Hotspot later on to optimize that on AVX512 if we so wish to use the mask registers. I do not know what the technique will be in the future, but that may be one way to do it. Another form of operational composition is essentially rearrange. This is an operation on vectors that will allow you to permute, rotate, shift, and reverse elements. So you get an array of indexes, which we call a shuffle. You pass it to rearrange, and it shuffles all the elements inside the vector according to your indexes. So we can build up all sorts of interesting operations in the vector API. We need to adjust our implementation to do exactly this under the covers. Okay, so I'm going to pass over to my colleague.
Thanks, Paul. So now that we have looked at the API itself, let's talk about the implementation. Only in brief, though. There is an excellent JVMLS talk delivered earlier this year, which has more in-depth discussion about the implementation, which I highly advise for those who are interested. So here's a disclaimer from Intel. So our goal with the implementation is to convert a Java code as shown on the left, which uses the vector API, to a highly condensed and optimized machine code, which uses the vector instructions. Anyone who is familiar with or has seen assembly code generated for Java would know that a single line of Java code generally generates multiple lines of assembly code. If you see in the Java code over here, there are a few method calls. There is a call to species.length, species.from array. So the generated assembly would have a call instruction. It usually gets inlined. However, there would be additional assembly generated for creating objects, initializing them, which you don't see on the generated code on the right. So our goal is to remove all the boilerplate code and extra data which is allocated by Hotspot. The challenge we have is how can we represent vectors at the JVM level? So as you know, JVM has primitive support for only up to doubles or longs, which map well to the underlying underlying register set. We don't have any primitive data type which would map to XMM register, YMM register, or any other register on vector register on other architectures. So that's why the API is designed using regular classes and methods. Well, things are going to change with value types. So if you guys attended the keynote yesterday, Mark showed an excellent demo about value types along with other demos, which I thought was pretty cool. In a sense, value types gives users the ability to define aggregate data, aggregate structures which would behave like primitives. There are many interesting properties to value types which make it an ideal candidate for implementing vector API. So since it forgoes object identity, there are certain operations which are restricted on value types. So you can't get a lock on a value type, you can't get an identity hash code, and so on. What this means is the object does not need to be allocated on heap. You can have the object allocated on the stack or on a register. At the same time, it gives you a nice flat layout of your data structure. Here's a slide explaining what I mean. So right now in the current implementation, a reference to an int 512 vector points to an object which has an object header and an array reference, which itself points to another object with an header, and the actual data follows it. With value types, you could have a flattened layout of your vector where all the 512 bits can be laid out contiguously in memory. We have experimented value types, and it looks very promising. But the problem is it's a little far out, and we don't have value types in the main OpenJDK trunk. So right now we have a different approach. The approach we use is we define typed vectors. What I mean is there is a vector class defined for every combination of type, which is byte, int, short, long, and so on, and every size starting from 64-bit to 512 bits. All these classes are well known to the JVM. So JVM, since it's aware of it, it can optimize it, specifically using intrinsics. It can replace method calls with special vector instructions and also place the data inside vector registers. So in effect, we get the mapping which we desired. Intrinsics is a well-known mechanism which is used to replace method call implementations with special hand-coded optimized implementation. It's used currently for many common JDK methods. To name a few, there is system array copy, object.hashcode, etc. So similarly, we have intrinsics defined to convert vector API calls to corresponding IR nodes, which represent the same semantics as the method call. So let's look at an example here. Here's a piece of Java code where it iterates over an array in strides of length, spec.length. And within the body, it creates two vectors by loading 16 floats, 16 floats in vector 1, and 16 floats from array B into vector 2. And following that, performs an addition and stores the result into an array. So when this piece of code gets intensified, Hotspot can recognize the vector API calls. And it would, along with other optimizations, it can replace the vector API calls with special nodes which we have defined. So as shown here, spec.length is replaced by a constant integer node. It's constant because the length of a species can be determined statically. Similarly, from array generates a load vector node, and the add operation generates a vector addition of vector float node. And the output for the load vector is fed into the addition node, and finally we have a store node to store the result into the array. There's a small hiccup with intrinsics. Like I mentioned before, we have vector classes defined for each combination of type and length. So that's a total of 24 classes. And each class has roughly 30-odd methods defined for it. So that would mean we need to define and implement a lot of intrinsics. So the approach we use is to define intrinsics for a particular flavor or a particular category of operation. So we categorize the applications into unary operation, binary operation. There are some shuffles, broadcasts, and so on. So here's an example of a binary operation, which operates on the two operands passed here, op1 and op2. And if you look at the notation, it's a hotspot intrinsic candidate. So binary op, as its first 4 parameter, it takes the operation which is to be performed, followed by the vector class and the element type and length. So these 4 parameters, it's crucial that these 4 parameters are constant so that the JIT will be able to replace the binary op with a vector node corresponding to the operation being performed. And following that, there is the actual vector operands. Here's an example of how add is implemented. So the add method on a int 512 vector, it delegates the processing or delegates the operation to a binary op method. And it passes the operation ID, which is an add. Then it passes the class, int 512 vector class. It passes the type, which is an int, and the length. And when this code, when add is compiled, C2 can identify, it can intrinsify binary op to a vector addition of vector integers. It's a addition of vector integer node. If you see here, after an addition is performed, there is a box operation, which basically wraps the vector value into an ordinary object, so which is of type 512 vector. Similarly, we have defined intrinsics for all different categories of operation. So as compared to like hundreds of intrinsics which we need to define, we only have a handful of intrinsics. As a final step, the C2 generates the corresponding vector code for the vector nodes. So here's vector add being generated for the vector vi node. This is a simple example of an add which has a corresponding add instruction in the machine. But at the same time, we have transcendental functions defined, such as logs, sine, cos, and so on, which don't have a corresponding machine code. So for implementing those, we have used the SVML intrinsics, which are part of the Intel C++ compiler, and we have generated those are the optimized, highly optimized sequence of code, and we have used so as the when machine is when the machine code is generated for such operations, you generate the SVML intrinsics. Every intrinsic takes a default implementation. That's when you run on a machine which does not have the vector instruction set, or when it runs in the interpreter mode. So the default implementation takes a lambda, and the binary operation in turn calls the apply function on that lambda. Vector box elimination is a very crucial step to get the tight optimized code which we talk about. So as you know, since vector objects are like just like regular Java objects, we have to wrap every vector value inside an object. And anytime we want to do any operation on vectors, we have to extract those values from objects. So we insert vector unbox operations whenever we have to extract value from a vector object, and we insert vector box operation when we wrap a vector value inside an object. And later, we do some transformations to identify which of the boxing and unboxing operations are required. And the operations which are not required, we remove the dependency on them. So at later stages of the compiler, during escape analysis, it can basically stripe away the unwanted boxing and unboxing which is generated. Okay, now we'll look at some more examples. So here's an example of Sepia Filter using Vector API. So as you can see, you load the red, green, and black values into vectors. Following that, you apply some multiplication and addition operations to get the result into the 3 vector registers, vector objects. And this is the saturation step, where you can see the use of comparison to generate a mask and a blend. So this essentially, so all the values, if they are greater than C10, it's replaced by the constant C10. Here's the generated code for the Java code shown before. So as you can see, there are vector mul and vector addition operation generated for 256-bit vectors. So there is a pre-recorded demo I have, which I have run on my laptop machine, which has a Skylake processor. So here there are a series of images, and there are two multiple threads running the scalar code and the vector code. So the middle row is the vector code applying the Sepia transformation, and the row at the bottom is the scalar implementation. So as you can see, the scalar code is quite a bit slower than the vector code. And the difference is somewhere around 12 to 13x. Let's look at another example. So this example, again, is borrowed from a blog written by Richard Starting. He has many nice examples where he has experimented with Vector API. So in this code, we do a dot product of 2 arrays, left and right. So we stride over the arrays on 8 bytes at a time, and load 8 bytes into left to L and R, and do a FMA and gather the sum into the vector sum. So the second iteration would similarly load the next 8 values and use the same sum to accumulate the result. And in the end, once you exit the loop, you do a add all on the values in the sum and return the result. So the code for a dot product looks something like this. So there is a vector FMA add instruction generated. Well, there are 8 of this here. The reason is this hotspot decides to unroll this code 8-fold, and that's the reason we have 8 FMA add instruction generated. However, there is some performance left on the table here. The FMA add has a high latency, and if you see, each of the FMA add instruction accumulates into the same YMN register. So because of dependency, one instruction depends on the earlier one. So to remedy that, you could unroll the code yourself. So instead of having a single sum vector, you could have 4 sum vectors and do FMA operations on those 4 sum vectors. And in the end, you sum all of them together and return the result. If you look at the generated assembly here, there are 4 FMA add generated corresponding to the 4 FMA operations in the loop, but they have different YMM registers used for accumulating the results. So by doing this, we are able to mask the latency, and you get the best performance using this version. Here's the performance on a Skylake desktop platform. The Skylake server. The base case is the scalar code without using Vector API. The yellow bar shows the speed up we get using Vector API, but without any unrolling. So there is a 2x performance gain. But when you unroll the code and mask the instruction latency, you get a 4x speed up. And when you double the vector size to 512 bits, you get an even higher speed up of 5x. Similarly, FMAs can be used to refactor scalar matrix multiplication into a vectorized version. So without going into the details of the code here, I'll straightly jump into the results. So with respect to the base case using scalar operations, when you use 256-bit vectors, you see a performance gain of 3x. By using 512 vectors, you see a 5x performance gain. Another example here is a Mandelbrot, which demonstrates using vector API for complex number computations. So in this code, I would like to point out the use of the comparison operation to generate a mask which identifies which of the complex numbers have converged, so that only the complex numbers which haven't converged can participate in the computation further. So another demo to demonstrate the performance. So here's the scalar version as compared to the vector version. So as you can see, the frame rate which you get for Mandelbrot is somewhere around 4 to 5x. So we are working on experimenting or contributing with different vectorized implementation of common BLAST routines. Here's the current status. So as Paul mentioned, it's incubator JEP. The JEP number is 338. We are working with the community to review the API and to review the implementation so that we can have this as part of the mainstream JDK in the upcoming release. So in conclusion, we would like to request you guys to give it a try. You could download the build and build it on your platform using the link shown here. You can participate by experimenting with the API and vectorizing your code. And if you have any feedback, you can reach us at the mailing list here. That's it. Thank you.
Any questions?
Almost certainly going to sound really dumb here, but I don't know the impact on the generated bytecode of indirection. And I was looking at the dot product code, and my first thought was, could you genericize that? If you knew what types of your arrays you had, could you write a method that did this once and then use it any place you wanted to use dot products? Or is there a good reason that trying to do that would totally eliminate all the benefits you're trying to obtain?
I'll let Paul answer this, please.
I'm trying to understand the question. The question was, can you write a generic dot product method, say in Java, that people could use and just pass in the float or double arrays to it?
Exactly.
So the implementation of that could use vector API, and it could use all these tricks like unrolling or FMA and express the sort of accuracy of the result. It could do exactly that. And that's exactly why it's targeted towards advanced developers who can write these things, and they don't have to rely on intrinsics in Hotspot to do it. They're in control of it themselves, and they can write a matrix multiplication library or a BLAS library using these techniques. That's exactly right. I mean, another alternative is to write JNI and go to use the BLAS libraries in C++, but for portability across stuff, you can do that. So there could be libraries like that, and the question is, should it be in the JDK? Probably not, because if they have this API, the developer is free to do it in whatever way they want. And there's a whole bunch of algorithms that could be expressed, not just dot product, matrix multiplication, hash codes, cryptography, even parallel binary search. You can do that too. It's quite funny. Yep.
AVX 512 in particular, as well as other AVX sets, are known to slow down CPU frequency, to turn down CPU frequency if used heavily. Which means that if I have a Java process that's running, let's say, a server that runs multiple GVA, let's say, instances,
So maybe I need to verify this, but AVS find that if AVS 512 is used frequently, then the frequency is lowered because of power and performance, power reasons. But if I'm right, it lowers the frequency of a core. I might be wrong about this. Would.
Yeah, and it's not just Java. That's any process that's doing these types of AVX. Yeah. 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 I would say also when you're doing these types of computations, you could also use get all your vector units operating at 100%, but get all your threads operating at 100%, because you can parallelize this using parallel streams as well as a vector API at the same time and really crank up the usage of your electricity if you wanted to get even better performance. And in those cases, when you're using parallel streams, it's going to fight for resources whatever is on the box, and it's going to aggressively try and use it. So when you're doing these types of computations, you really want to ensure that you have the machine to yourself, or at least isolated per cores, in terms of ensuring that there's no busy neighbors around you. And that's a challenge for perhaps virtual machine cloud technology like AWS, but if you're not using a bare metal sort of container or machine, you're probably going to end up with noisy neighbors here. So the performance requirements, if you're going to do this on cloud, you really want to, my feeling is you really want a bare metal cloud infrastructure to make that work correctly, or as fast as possible. Yeah. Yeah. Another question over there. Let me repeat the question. How does it work with Graal? Is that, yes. It doesn't at the moment. I hope that Graal will follow it, and there may be other jets like the Azul Falcon, for example.
I'm jumping ahead. We talked about Falcon tomorrow, but since we are based on LLVM and Intel contributes very heavily architecturization usage of AVX 512 and structure scheduling to LLVM, we get to leverage it. So yes, our JVM already uses AVX 512 a lot, and we got it pretty much because of the awesome work on, I should say, on LLVM.
I think from the Graal point, if this gets into the JDK, the Graal team will implement it. And they'll apply whatever techniques are applicable to Graal to optimize to produce similar results. Yeah. Okay. Thank you.
Thanks.